Robots today can lift dozens of kilograms, sense force, and recognize objects. But why is a single egg enough to make them fail? The problem is not strength. It lies in something far less obvious. Why do robot hands have strength but still lack real tactile feeling? The core failure point of robotic hands does not lie in mechanical strength or the number of degrees of freedom, but in something far more subtle: the resolution of tactile sensation. The human hand is not merely a gripping tool. It is a living sensory surface with an information density that far exceeds any artificial system available today. When a robotic hand is placed next to a human hand, the largest gap is not gripping force, but the ability to know exactly what it is touching. Human skin, especially at the fingertips, contains roughly 17,000 tactile receptors distributed at extremely high density. These receptors do not work in isolation. They cooperate tightly, allowing humans to perceive pressure, vibration, microslip, and surface texture simultaneously. This is why we can hold an egg without crushing it, sense that an object is about to slip before it actually does, or distinguish cold metal from warm plastic in an instant. This is not AI, but pure biology, optimized through millions of years of evolution. By contrast, most robotic hands today still rely on global force or torque sensors, or a small number of discrete pressure sensing points placed at the fingertips. These sensors can measure force, but they cannot form a continuous tactile field. In essence, the robot knows whether the force is large or small, but not how that force is distributed across the contact surface. This creates massive tactile blind spots, areas where the robot has no information at all, even while physically touching the object. This difference becomes critical when it comes to microslip detection. Humans do not wait until an object falls from the hand to react. High-frequency vibration receptors in the skin detect tiny oscillations as soon as friction begins to change, allowing the nervous system to adjust grip force almost instantly. Robots lack this advantage. In many cases, the system only realizes something is wrong when the object has already slipped or is about to fall, at which point any corrective response is already too late. This is why robots often grip either too hard, damaging the object, or too loosely, dropping it. The problem is not only the number of sensors, but also multisensory integration. Human skin does not just measure force, it simultaneously senses pressure, vibration, temperature, and even pain thresholds. All of these signals are processed in parallel within a soft, thin material that naturally conforms to the contact surface. Robots, by contrast, are forced to use separate sensors for each modality, making the fingertips bulky, complex, and difficult to integrate. Physical space is limited, and every additional sensor comes at the cost of durability, size, or reliability. Even the most advanced efforts, such as electronic skin, have yet to solve this challenge. Current e-skin technologies face a fundamental trade-off. If they are made soft and elastic, like human skin, durability and lifespan drop sharply. If they are robust enough for industrial environments, they become too stiff, losing the ability to conform and transmit subtle signals. Moreover, increasing sensor density means more wiring, more complex circuitry, and higher susceptibility to signal noise, turning the robotic hand into a fragile system rather than a reliable tool. The final result is a familiar paradox. Robots have strength, mechanisms, and algorithms, but no true sense of touch. And in the physical world, lacking sensation means lacking control. This is the silent killer of humanoid robots, a seemingly small hardware limitation that is enough to derail the entire ambition of replacing the human hand in tasks that demand high levels of dexterity and finesse. In your view, where is the biggest bottleneck for robotic hands today? Tactile sensors, electronic skin materials, or signal processing and reflex speed? Leave your thoughts in the comments below. Why can robots feel contact, yet miss the critical moment to respond? Even if we assume that robotic hands are equipped with sufficiently advanced tactile sensors, the core problem remains unresolved. The robot's processing and response chain is simply too slow to reproduce the natural reflexes of the human hand. In the physical world, sensation only has value when it is paired with timely reaction. And it is precisely here that humanoid robots lose at a fundamental level. In humans, grasp reflexes occur within roughly 20 to 50 milliseconds, and crucially, many feedback loops do not pass through the brain at all. When an object begins to slip, microvibrational signals are processed directly at the spinal cord, triggering an almost instantaneous increase in grip force. This is a distributed, highly optimized, and extremely energy-efficient control system. Robots have no equivalent of a spinal cord in this sense. In robots, even the simplest reflex must pass through a long pipeline. The signal is first captured by the sensors, converted into digital data, sent to the central processor for analysis by control algorithms, and only then translated into commands that drive the actuators. Each stage introduces latency, and when combined, total delay can easily exceed 100 to 200 milliseconds. In delicate physical interactions, this is an eternity. By the time the robot understands what is happening, the object has already slipped, deformed, or fallen from its grasp. The problem becomes even more severe when considering high degree of freedom control. A robotic hand does not merely open and close, it must coordinate dozens of small joints in an environment where friction, deformation, and non-linear contact conditions are constantly changing. Each finger affects the others. A small change in force can trigger cascading effects across the entire system. What humans handle instinctively, robots must model mathematically in real time, an extraordinarily computation-heavy task. Machine learning models for tactile control are often presented as the solution, but reality is far more complex. Tactile data is deeply physical, difficult to generalize, and highly dependent on object shape, material, and surface state. A model trained to handle a plastic bottle may fail completely when grasping a thin glass cup. When conditions change, the model does not adapt intuitively like a human. Instead, it often collapses or reacts too slowly. There is also the issue of wiring and signal noise. To increase tactile resolution, robots require hundreds or even thousands of sensing channels across the fingers. Routing these signals through complex moving joints creates major challenges in cable management, electromagnetic noise, and long-term reliability. When input data itself becomes unstable, every downstream algorithm is compromised. The end result is a clear paradox. Robots can sense more and more, yet respond more and more slowly. And in physical interaction, slow reflexes not only destroy naturalness, they also destroy trust.